All right, let me go and get going here. Actually, let me go ahead and check. I haven't had a chance to make certain that the links are working for the current assignment. Get this accepted here. All right. All right. So let's start with kind of the usual. Just make sure everybody's on the same page here. So we're getting close to the end here. We are going to be starting on kind of a bit of a new topic, like I've been mentioning. So beginning of this week, we'll look at PCA. So we'll look at some different unsupervised learning techniques. Mostly we'll concentrate on dimensionality reduction using PCA, and we'll also look at a little bit of some clustering. So both of those are really useful things to have in your bag of things that you know how to work with, basic kind of stuff. So So I had some of these names wrong on the notebooks, but basically looking at we're calling it Unit 13 here, the PCA, and there, Dr. Ng also does have some materials on this as well. So as usual, I think he does really good on this. So I definitely recommend. I'll check his notebook here as well, see if my links are still working. Since they kind of changed the location of a lot of his lectures on YouTube, but yeah, I don't have any video that I've made this week or next week, so it'll mostly be these that I'm doing here in class, or in Dr. Ng's videos if you want to go through this stuff. So, and then next week there should be also a thing on unsupervised learning, which is mostly on clustering and stuff. So, and then really. I am planning on, so there's just 3 more weeks of classes here, just to remind people. So we're going to be doing that for the next 2 weeks, and then that third week, which is the last week of classes, we will be having the second test 2, which will be comprehensive. I'll talk more about that once we get closer to it. So, but yeah, there's just this one more assignment, 6. And over unsupervised learning, we'll spend the next 2 or 3 weeks talking about that, and then kind of maybe wrapping up and doing some review and stuff on the third week. Although that's not completely the end of the course. So also don't forget about the project. Like I said, I'll keep mentioning this. So hopefully everybody's working on this, keeping this in mind. So I'm going to be leaving finals week to look through those and evaluate those, and but you should hopefully have most of your stuff done before the finals week of class, or at least be pretty far into getting your data set and doing exploration on it, and coming up with some modeling and stuff. So hopefully also, as you look for these last 3 weeks here at unsupervised learning, you'll get kind of a feel, and maybe you can go back. So unsupervised learning can be used in a couple of different parts of the workflow for a typical data analytics project. So it can be helpful on the data exploration for understanding your data. It can be useful sometimes for doing some data cleaning. So especially orienting your features and maybe potentially reducing them down to a more important subset can sometimes have some benefits. So something to keep in mind while you're working on your final project. You might want to look at those. They can give you some insights on your data as we're looking on the unsupervised learning for the last 2 weeks here. So all right, so the assignment it is live, so I was able to was able to accept it. Let me go ahead and clone it here. So maybe I'll kind of start with that. So give me a moment to get this on my locally here. All right, so let's see. Once building that container, yeah, and I am still working on the assignment 5s. So I didn't get them all the way done like I was hoping to. So I'll try to get those back, and we'll do some discussion on that once I've got those returned. So the few people I've looked at so far, again, I think most people probably did well on the assignment 5, so I don't anticipate too many issues on it. So, but we'll review that once I get it back. But yeah, so we've got the assignment 5, and then just the assignment 6 are all we've got left on the class here. Yeah, okay, so yeah, it's going to take some time on that. While that's coming up, I was bringing up the assignment 6 just to make it certain it's there. I'll just kind of do a quick overview of it. You should be turning your attentions to thinking about the assignment 6, get it accepted sometime this week. Start looking on it here. So it'll take a little bit of time to get up. So let me start talking a little bit about principal component analysis then. I guess maybe I'm going to have to bring up the textbook real quickly. So let's see here. Okay, so yeah, we are basically, for the last 2 weeks, kind of following the presentation in the textbook where they go over the dimensionality and talk a little bit about high dimensional data for chapter 8. So we'll look at that this week. And then next week we'll look at, mostly I'm going to concentrate on the clustering kinds of things. So the first part, the chapter 9, we'll talk about basically doing the k-means clustering. And then the after that I've got something kind of called advice on machine learning. I just mentioned that hopefully everybody does have the textbook. This is a good general book to have just for reference and things. So. But the Appendix B material, where it kind of goes through an example machine learning project checklist, is kind of the stepping up point. Also, hopefully I've mentioned that in the description for the class project, but that's a good kind of reference to think about your own kind of stuff you ought to be doing on your class project. So if you haven't looked at that appendix, you might want to take a look at that. So, but that's kind of the reading as well as reviewing for test 2 that we'll be doing on the last week of classes here. So, all right. So I'll come back to that once that's up. And I'll bring up the lecture notebooks just based on this material and Dr. Ng's stuff here as well. But just so we can do a little bit while I'm building my containers there for the last assignment, I'll mention a few things getting started off on this. The chapter 8 is about dimensionality reduction. That's the title of it. So the idea idea of this is what we're talking about in terms of dimensionality here is whenever you're doing data analytics, the features, so the columns of your data set, the way we normally lay it out, those are the individual features that you use to build a model with. All right. So in mathematics, we think of those as dimensions of the data set. Okay. So we can't visualize stuff past 2 or 3 dimensions, but if we could plot each one of the rows of a data set as a point in some high-dimensional data set where each of the different axes of the high-dimensional data set would correspond to one of the features, one of the columns that we have, right? So that's how we're using dimensionality here. So typically in the data sets that we would be using, nowadays, and even for your guys' class projects, I wouldn't think of it as unusual to have hundreds of dimensions, if not more. So for real work out in the world, academia or industry, tens of thousands, millions of features of dimensions is not uncommon. So big data sets will have that number of things to work with. Okay, so that gives both benefits, but also challenges that you have to get around and work with. Okay, so for one, I don't know how much I'll go into this, but if you did the readings here, the curse of dimensionality, there's some kind of non-intuitive stuff. So if you approach this from the mathematics side, you can begin to understand some of the weird stuff that happens when you're trying to build models in truly high-dimensional spaces. I think that, let me see here. Well, I just... I guess I'll just mention a little bit the discussion here, trying to give an intuitive feel for why there can kind of be a difference in, so this is not just a difference in degree, but kind of an actual difference in the absolute way that things work. So when you're in a low-dimensional space, if you pick, so like in one dimensions or 2 dimensions, like it's shown on the figure 1, if you pick a point at random, like on 2 dimensions in like a unit squares, which is what's being talked about in the example here, you have a relatively low chance of it being close to one of the edges, 0 or 1 basically. Because where you can define close however you want. So our textbook talks about close in terms of being 1/1000th from the border, right? So you only have if you're picking something at random. So if you generate a random number from 0 to 1, where you have a uniform probability, you only have a 1/1000th of a chance of it being 0.001 or less, or 1/1000th of a chance of it being 0.999 or greater, right? So just 2/1000ths of a chance of it being within that close to a border. But you have to do that for 2 dimensions. So you have only 2 chances that it's 1 in 1,000 or 2 in 1,000 within that, being real close to like an edge there. Okay? So anyway, in 2 dimensions, picking a point at random where the randomness is uniform, it's very unlikely that any of the points that you randomly generate are with that close to the border, the 0.001 from the left or the right edge or the top or the bottom. Right? Until you have a large number of points. So if you have 1,000 points, since there's, I'm approximating here a little bit, but it's around like 1 in 1,000 chance that you will have something that's that close to the edge there. So once you have 1,000 points, though, you're likely to have one of them that's in the range there, but only one, right? But when you end up with going to higher dimensions, so if I have thousands of dimensions or millions of dimensions, if the features are relatively randomly and evenly spread throughout that, you're very likely that at least one of your features, since you have so many of them, ends up near an edge. And if you're generating them randomly, where I have a 1 in 1,000 chance for like one or two features to be near an edge, if I have 1,000 features, if I'm generating things, using a uniform random distribution, I'm likely to have at least one of my 1,000 features be near the edge. So every point will be at least near one of the, close to 0 or close to 1 in a high dimensional space. Right? And it gets even worse, of course, when you have more than 1,000, when you have millions of features or something like that. So. And anyway, so that has some consequences in terms of modeling and stuff. And there's some other things in here. So the way that things normally work in high dimensional space is when you have a high dimensional space, it's really big. Any space, if the features are real value numbers, is infinite. But in a sense, so what's normal in a very large data set that's high dimensional is it's going to be very sparse. So the actual location of your samples that you have are going to be clustered in relatively small areas of the total space that you actually have for all of your features, all of your dimensions that you have. So that also, intuitively, maybe for some people, that makes it a lot tougher for most, for all of the mechanisms that we've discussed in this class to build a model and to make predictions. So they'll just be less reliable. It'll be easier for them to build models in lower dimensional space because usually your samples in that space will be much more dense. They won't be so sparse and spread out. So your models can be more representative. But once you get to high dimensional space, you're much more likely to have data that you're going to see in the future that you don't train with, that's in some other part of the space that you've never seen before. Okay, so if that makes sense. So, and you can always combat that a little bit by having really large data sets. So even though it's high dimensional, if I have billions of data sets, I can fill in some of that sparseness, and I'll be more likely to have things representative of any new data that I might not have seen before in the future, right? So that can help some, but it won't completely remove or ameliorate these kinds of problems that you have with high dimensionality, okay? So just to summarize that on the last paragraph here. So one solution when you have truly high dimensional data space is increasing the size of the training set until you reach sufficient density. Of course, and that's not always possible, though, right? So, as a data scientist or as an experimental scientist, we always want more data to be able to get better models and make better predictions. But it's not always possible to collect more data, or it's not always possible in industry to have a process that we can easily add more data to the thing that we need in order to build some sort of production model or something. So one approach might be these kinds of dimensionality reduction then. Using mathematical techniques to take a high dimensional space and represent it in a much lower dimensional space, in a much lower number of features. Okay? So, and if you've never thought about this before or come across this concept, you might be surprised that you can do that, but there are common techniques. I'm mostly only going to talk about principal component analysis, although, I will go maybe through a bit of just touch on some of the other stuff that's talked about here and the main approaches. But after that, for our assignment, we're mostly going to just use PCA. It is probably, by far the 95% of the time that people are doing this kind of dimensionality reduction in machine learning. They'll be using PCA or something like that. Anyway, so before I jump into that, let me just jump back to the assignment since I finally got this up and running here. Okay. And as usual, we'll come back to this more than once here, but I'll just get started on this. So on the current assignment, yes, there's actually two parts. So one part we asked you to do a clustering using k-means. So that's really kind of the next week's stuff. And then the second part is really doing principal component analysis here. So we'll talk more about clustering next week in more detail. The basic idea is that for unsupervised learning, you might have a data set like this. So this is the data set for the assignment. That you should need to load in. So the assignment has the workflow, same workflow that everybody should be familiar with at this point. So we've got tasks that you need to complete in the source subdirectory. So including starting out by loading the data that we'll be using for this assignment here. But for clustering, the basic idea for like k-means, which is the also, it's kind of the most common sort of clustering approach that is used if you look at machine learning. The idea is for unsupervised learning, you've got a data set where you don't actually have labels for the data. So in a classification task, visually, if we see something like this, it looks kind of like there's three areas in this two-dimensional space. We've got feature x1 and x2 here. So it kind of looks like there's three kind of clusters, like one down here is maybe one category or class, one over here maybe, and one up here. I mean, that's not necessarily 100%, but it does kind of look just visually like that might be the case. There's kind of three classes, three clusters in there. Right? So that's the usefulness of this kind of a clustering is if your data isn't labeled, you can have it label it for you, kind of discover clusters. So when you're discovering clusters, you're really discovering classes for like a classification task, potential classes, right? So these may or may not be useful. And of course, if you're talking about data that has more than two dimensions, you couldn't visualize it like this, so you'd have to use other measures to see whether you think you've gotten kind of the right number of classes or not. Which we'll talk a little bit about if you do the readings next week on clustering. But yeah, the first one is we'll do this k-means clustering. I'm going to actually have you implement it by hand. So k-means clustering is simple enough that you can write an implementation for it. So there is, scikit-learn supports k-means clustering and other kinds of clustering approaches as well. But k-means is simple enough that you can write the basics of it. So I'll go into more details of that, but that's kind of what the first task is. So there's a couple of functions you have to write to find the closest centroids, and then compute the centroid means. And when you have those functions, you can basically iterate over that to cluster your data. And then the second part is to do a PCA. So we're actually also going to have you implement principal component analysis by hand as well. Okay, so yeah, I do need to discuss a little bit today, probably Thursday. We'll talk more about more of these details on Thursday. But PCA uses basically techniques from matrix algebra. So we're going to be using singular value decomposition in order to implement the basics of principal component analysis by hand. Okay? So yeah, we walk you through that. It shouldn't be too tough for most people to get the basics of this working here. So again, on the second part, we write some functions to do some feature normalization and scaling, and then the main heart of this is the PCA that you write by hand is going to be basically calling a method from scikit-learn's matrix library to perform the singular value decomposition. And again, scikit-learn has a PCA method, but it is relatively easy enough to implement the basics of it. So that's what we're doing for the assignment. And then the last thing is we kind of compare the results of what you do with we project a high-dimensional data set onto 2 dimensions and then reproject it back, so recover it in this here. All right, so yeah, we'll come back to more details on the assignment, but let me get back to talking about principal component analysis so we can at least get up to the part, some of the stuff that we should be familiar with to do that second part, to do the PCA by hand. So let me get my get my lecture notebook folders open up here now. All right. So yeah, I might have had some of the names wrong on the announcements initially, but I'm going to start off with this one here. So this material is mostly directly from the textbook, the chapter 8. Yeah, I wanted to, let me just check real quickly. And there is 2 notebooks from Dr. Ng on principal component analysis and unsupervised learning, although they're in reverse different order here. So yeah, I think those links, hopefully I had all those up to date. I'd gone through those later on. So these links to all of his treatment of PCA look like they are working right now. So. All right. So yeah, the lecture notebook doesn't have a lot about the section on the discussion on other kinds of approaches to dimensionality reduction. I just mentioned a little bit. So yeah, there's kind of two main things. Principal component analysis is really a type of projection, but there's also the textbook discusses briefly manifold learning. Both of these, all of these are available in scikit-learn. So you can do PCA and other kinds of projection, or you can do like a manifold learning to do some dimensionality reduction. So just to kind of briefly go through these, I don't know if this figure is real easy to see, but the basic idea of dimensionality reduction is, so here we've got three-dimensional data, so generically features x, 1, 2, and 3. And if we want to project that down into 2 dimensions, so 2 dimensions is a plane. So the light gray plane here, it's not orthogonal to any of the 3 dimensions like this. So what I mean by orthogonal is it's not in a right angle. So it goes off in an angle, a non-90-degree angle to all 3 of the dimensions here. Right? So the idea of doing a projection, and this is basically so if we, PCA is kind of about selecting the plane here. In this case here, so we're not talking about that. We've just selected a plane for some reason, and we want to project our data down into that 2 dimensions. So this plane, if you know a little bit about linear algebra, and I won't go into a lot of the linear algebra, just some of the basics in order to do the singular value decomposition stuff we'll talk about this week here. So, this plane, though, in the original 3-dimensional space, we could define that as basically 2 vectors here would define our 2-dimensional plane we're going to project onto. Right? And so for various techniques, if we wanted to project this data down onto our 2-dimensional plane, we could do that. Right? So we'd have to have something that would project it in all the 3 dimensions onto the closest point. So what's trying to be represented here is the projection is going to have the smallest distance. So whatever the line is that gives the smallest distance from the point to some point on the plane is what's being selected here, and that will be our projection for each one of the original 3-dimensional points onto the 2 dimensions here. Okay. So, and the whole point of principal component analysis is in many data sets, we can select a lower dimensional plane, a lower dimensional representation to project our original high dimensional data onto, where we lose very little information in the projection. Okay, so in this case, again, this figure is meant to imply that even though the data is in 3 dimensions, all of the points lie relatively close to the 2 dimensions of this plane that's being illustrated here. Right? So when we do the projection, we're not really moving. We don't have to really move any of the points very much to get them projected on the 2 dimensions, and we reduce our original problem from 3 dimensions to only 2 now. Without very much of a loss of information. Right? So in theory, and that's what, to jump into what PCA does, it's a dimensionality projection technique, but what it is doing is it's finding the best sort of lower dimensional representation that will lose the least amount of information in the higher dimensional space. Okay? So, again, you can't really visualize this once you get beyond 3 dimensions, but you have to imagine, if we had thousands or millions of dimensions, I might want to project 1,000,000 dimensions into the closest 1,000 dimensions, so reduce it by a factor of 1,000. Okay? And that, and PCA can automatically calculate, okay, so if I want to make that much of a reduction, what is the best 1,000-dimensional hyperplane to use that will give the least amount of loss of information from my projection. So yeah, this projection here and the way PCA does that is it really is perpendicular to the plane. So whatever the plane is that's lower dimensional, the line that goes to that plane that's going to be the smallest line is going to be the one that's perpendicular to the plane that we have. So yeah, this presumably is this. This projection here. So you can see it a little bit in the three-dimensional figure, but now you can kind of see if you project it down. And again, Z1 and Z2 are not the same as any of the three original axes that we had before. So these are two new axes that we projected the original data set down onto. But yeah, the only thing I'll kind of say about kind of the manifold learning is sometimes so when you're doing a projection like that, you are selecting a plane or a hyperplane. But sometimes the best projection would be into a space that's not really planar. And that's kind of what manifold learning is. This is a little bit, this is beyond this course. But manifolds is a mathematical term, and it is possible to mathematically find what's known as a manifold that would again have some of the properties that we're talking about that would minimize the projection, so would keep the most amount of information. Okay? But the manifold isn't going to be kind of like we're implying here, just a set of vectors. It's a more complex kind of thing that needs to be represented when you do manifold learning here. So yeah, the point of this, if you didn't do the readings, is in the one case, we're showing what would happen for projection for that kind of data like that, where it's kind of really a two-dimensional rolled-up shape in 3 dimensions. When you project it down, you get a lot more of mixing, so you kind of doesn't do as well if you project it down to the best plane of that, versus if you could just keep sort of a bendy two-dimensional thing, but like a roll that you project onto is kind of what happens over here. Okay. But let's jump to principal component analysis. So I'll go into the basics for the rest of the time that we have in here today. So the rest of the notebook, so most of the notebook's really getting into PCA. So let me see if this notebook is running here. So, oh yeah, but I'm having problems like this as well with the plotting here. So if I had it set to do inline plotting, you might need to uncomment that so it does. So it tries to do the plot in the notebook. Okay, so in the example here, and this is meant to follow the discussion in the textbook. So we're going to be using this data set here to illustrate principal component analysis and projecting this data set down to from 2 dimensions down to 1 dimension. So that's kind of the simplest case that we can do here. So here, we've got data that's in 2 dimensions, and again, these are just generic, so, this is a artificially generated data set here. For one, the basically what PCA does is it wants to find the first. So if we're going to project down into a lower dimensional space, or if we're going to reproject into a different dimensional space, we want to start by finding the first dimension that has the most amount of variance. So I won't be able to show this in the video, but the basic idea intuitively, so you don't have to really understand all the nitty-gritty of how the singular value decomposition works to find this out, but conceptually all that happens is of all of the possible first vectors, there's kind of obviously one vector that's like in this space here. I'll project it from the origin, 0, 0 here. So the one that goes kind of from here to here, you can kind of see that if we projected all of these points onto that line that I'm specifying here, they would be the furthest apart. Okay, so that means that this vector here in this space is keeping the most information that we have, as opposed to any other vector, right? So slightly, if I slightly, like for example, if I do the vector that goes straight up, and think about projecting that, the points at the end won't be as far apart as they would be if we projected them orthogonally onto the vector that I'm indicating here, right? So that is actually what happened here. So we actually did a PCA, if you followed this notebook, from scikit-learn on that data set. And we're still projecting it into 2 dimensions. So we have 2 dimensions, we're projecting it down into the same size data space, okay? So we're not reducing the dimensionality. But the result of that projection of that data, if we, and then what we show on the first figure here, is, so the result of doing the fit here, we call this X2D. So this actually projected it into a new two-dimensional data space. So we've got features 0 and 1. So the original X had 2 columns, 2 features, 0 and 1. And we've still got the 2 columns 0 and 1 after projection, and we can get access to those columns using slicing for the NumPy array that's returned back from the projection. So this, we're doing the usual. We're plotting the column 0 for this projection, the column 1 for this projection as our dimension 1, dimension 0 dimension, as our X dimension and Y dimension here, right? So you'll see that it basically rotated it. So, from my indication from this was the actual data set that we used on the PCA here. And when you project it like that, the X dimension ends up being along that vector I was indicating here, right? So it preserved the most amount of variance. So you can see, for example, this point here, it got flipped, it looks like, but this point here ends up down over here, a little bit below where Y is 0. And this point up here is basically, no, I guess it didn't get flipped, so it just got rotated down there. And we have this one and these 2 like this. Yeah, no, it did get flipped, I think. So I was going to mention, so when when we only have 2 dimensions, there's really only, the only thing that's interesting is the first one. So if we'd had 3 dimensions, there would still be, after you pick the first most important component, so the first most important dimension in terms of variance, if this was a 3-dimensional data set, so all the rest of the dimensions that you pick have to be orthogonal. So they're always going to be in right angles to each other, right? So in 2 dimensions, there's no choice. So once you get down to the last dimension, it has to be the one that's orthogonal to all the other ones that have been picked so far. When we have 2 dimensions, when we pick 1, there's only 1 remaining one, right? So the second vector is going to be the one that's 90 degrees when we project this 2-dimensional data down here. But if this was 3-dimensional, I would actually have, this vector and the vector that kind of comes in or out of the figure there, and PCA would figure out which is the second most important dimension among the 2 there by doing the singular value decomposition, right? And again, that goes for any higher number of dimensions. So conceptually, what happens, if I've got 1,000,000 dimensions that I'm doing a PCA on, is the most important dimension that's selected first would be the one that has the largest amount of variance. But then of all the rest of them that are orthogonal, the second most important one would be selected to be the one that has the second most amount of variance, and so on, down to the least important dimension that you have. So they get ordered by starting from the first one. All of them are orthogonal to that first one, and the result from PCA is the dimension 0 is the most important one, and then dimension 1 is the next most important, the one that has the next most amount of variance, and so on, that happens here. Oops. Be lagging a bit here. Okay. And so another thing you can get kind of directly or for so once you've projected into this 2-dimensional space, we can easily so once we've done PCA into, which results in basically this new 2-dimensional space, we can easily project that down into any number of lower dimensions that we want to by just removing any of the other ones that we don't want. So again, so our projection is 2-dimensional, so we can only reduce it down to 1 dimension. But it's easy to do that, right? So when we have our new 2-dimensional space, which is represented here, all we have to do is use zeros for the other dimensions, which is what we're doing here. So we're getting the principal component, so column 0, feature 0. We're just plotting those locations, but we're using 0 for all the lower dimensions that we want to project down into. So the result would be that all those points there just show up on our 1-dimensional space now in the projection. So the projection, so technically we call that projecting to the first principal component. But the same thing would happen, can be done if my original data set was very high dimensional, thousands or millions of dimension, if I were to project down to the lowest 10 dimensions, I just keep the first 10 columns, because the first 10 columns would be the first 10 principal components of the result from the PCA. And everything else you can throw away or zero out if you're visualizing it. And that would be the orthogonal projections into the new space that we have here. All right. so let's see here. Yeah, so just to wrap up, so the last part here is going into some more details how this works. I'll leave that for Thursday. So I've probably covered most all of the rest of the stuff that's discussed here. What I hope people understand from doing the readings and going through Dr. Ng's lectures is intuitively what's happening with PCA, right? So it's not so important to really completely understand the mathematics of how this works. So we are, so we'll talk a little bit about this technique, the singular value decomposition, which does this basically. So, but conceptually, all that's happened when you do a PCA is it's identifying the access. So if you were doing it by hand, you would kind of do it sequentially. So you would start by finding the axis, like I was sort of hand waving on the first figure, that accounts for the largest amount of variance. So by that we just mean the axis where the points would be the furthest apart if we projected onto that axis. Once you have the first principal component, first principal axis, then I'm going to identify the second axis. Again, if we're much higher than two-dimensional, there's choices all the way until we get down to the very last axis where you have no choice because it has to be orthogonal to all the others, right? So after you've selected the first axis, the first principal component, among all of the other axes that are orthogonal to that, one of those axes will have the second most amount of variance if we were to project onto that axis. So that becomes the second principal component using this singular value decomposition and so on. So once you do that projection, dimensional reduction is basically trivial. So like I was saying here, like I was saying before, so it's saying a little bit here, but the thing that's returned back from PCA is the matrix where each one of the columns or each one of the features has been ordered from the most to the least principal component. So if I want to project down, it's really just slicing the matrix. So I just take as many columns as I want to reduce down into, and that will reduce it down into the lower dimensional first D principal components, whatever D is. So yeah, I'm skipping over some other things. So we'll talk about these on Thursday here. So SVD doesn't work unless you actually center and normalize the data first. So we have talked a little bit about scaling of data. So that's what we're talking about here. So a first step before you can perform the SVD, singular value decomposition for PCA, is I need to first scale all the data and center it. So this is important. So for every dimension of my original data set, it has to have a mean of 0. It has to be scaled so that all the standard deviations are the same. So we usually scale it down to a standard deviation of 1 and a mean of 0 for each one of the original features that we have before we perform the singular value decomposition. So, and that's what's happening on the first task for the assignment 6 is just writing a function that will do the scaling and normalization for a data set before we try to perform a singular value decomposition on it. All right, yeah. So I'm going to stop there for today. So the rest of this notebook, if you haven't read through it, is trying to go into some of the details of how that works, including some of the stuff will be pretty similar to what you do for the assignment. So because I think we even show doing it by hand here in the notebook. So a lot of this stuff is similar to what you're supposed to do for that other function in part 2 of the assignment, where we in part 1 as well. So where we're scaling the data, and once it's scaled, we're showing basically using the SVD function from the linear algebra library for NumPy to perform the singular value decomposition. So this is basically doing what the PCA does from scikit-learn, but doing it by hand using the SVD function from the linear algebra library. So. But I'll go through some of those details. But yeah, so now that I look at that, a lot of the stuff for your assignment is similar to the examples that's shown here. Although this example is only on a data set again that's two-dimensional here, so we could visualize the resulting projection and rotation that happens. All right. Yep. So that's it for today. I'll go ahead and stop there. So,
Okay.
yep.
Sorry.
Yeah. Sure. Questions?
So apart from maybe the access that gives the biggest variance for the data,
Right.
is there any other reason or any other criteria you could use to reduce the dimensions besides the one that gives us the largest variance?
Is there? Yeah, okay. So. Let me think. Trying to remember if our textbook maybe talks about some other. Yeah. So yeah, if you're interested, so I'm probably not going to talk about this in class, but there is some other things. So some of the other dimensionality reduction techniques that you can do in scikit-learn are using things different than the singular value decomposition. So, but yeah, I'm not as familiar with those. But yeah, so there's quite a few of them that you can do in scikit-learn. But yeah, just read them from there. So I would have to go back and kind of remember what the things are, the multi-dimensional scaling and stuff like that. But they are doing something different than picking the principal component. Slightly different ways of doing a projection. So. Sure.
I'll just one.
Yeah. All right.